You think you understand the quantum eraser, you have watched the videos, you have seen the diagrams with the beam splitters and the detectors labeled D1 through D4. You have probably picked a side. Either the experiment proves the future can reach backward and rewrite the past, or it proves nothing of the sort, because the interference only shows up through post-selection and no signal actually travels backward in time. Either way, you think you know what the experiment showed and what it means, and you have filed it away as a settled question with a known answer. It is not settled, and the reason it is not settled has nothing to do with the debate you have been watching. The argument between the retrocausality camp and the debunking camp is an argument about the first stage of an experiment that has more stages that were published, peer-reviewed, confirmed, and then never discussed again. There are papers sitting in Physical Review A and Physical Review Letters and the proceedings of European physics conferences with titles like Erasing the Present, Changing the Past, that have accumulated fewer than 10 citations in nearly 2 decades. There is a review article in Science magazine, one of the 2 or 3 most prestigious journals on the planet, that references unpublished results by the man who invented the quantum eraser, results that were apparently never formally written up. And there is a theoretical prediction, one that every major interpretation of quantum mechanics agrees on, that has never been experimentally tested, not because the technology does not exist, not because the math is unclear, but because, as far as anyone can tell, nobody wanted to see what would happen. The prediction is simple. Quantum theory says you can erase which path information, restoring interference. You already knew that. But it also says you can then remark that information, destroying the interference again, and then erase it again, and restore it again, over and over, with no theoretical limit. Each cycle retroactively changes what the signal photon's data means when you sort it. The past does not get rewritten once. It gets rewritten every time someone in the future decides to erase or restore the information. And if that process has no limit, then the past is not a thing that happened. It is a thing that is still happening, right now, being edited by measurements that have not been made yet. That is not what the YouTube videos told you. That is not what the debunkers addressed. And the handful of physicists who explored this territory published their results in journals where almost nobody found them. And then the field moved on, as if those papers did not exist. What you have been arguing about online is the prologue. The experiment was never finished. And the question it was designed to answer, the deepest question you can ask about the nature of time, remains open. Deliberately, conspicuously, inexcusably open. So forget what you think you know about the quantum eraser. The version of this experiment you have seen explained is the version physicists were comfortable with. There is another version, and it has implications that the people who understand them have, for the most part, chosen not to talk about publicly. To understand why, you have to go back to a postcard sent from a foxhole in Italy in the summer of 1944. John Archibald Wheeler was not the kind of physicist who stumbled into the deep questions by accident. He went looking for them. Born on July 9, 1911, in Jacksonville, Florida, he earned his PhD from Johns Hopkins at 21 years old, which should tell you something about the kind of mind he had. He went to Copenhagen to study with Niels Bohr, came back to Princeton, and spent the next several decades supervising 46 doctoral students. A number that becomes staggering when you realize those students included Richard Feynman, Hugh Everett, and Kip Thorne. Wheeler either coined or popularized the terms black hole, wormhole, quantum foam, and superspace. He co-authored the paper on nuclear fission with Bohr that was published on September 1, 1939, the day Germany invaded Poland. He worked on the Manhattan Project at Hanford, where he personally solved the xenon poisoning crisis that was shutting down the plutonium reactors and threatening to derail the entire bomb program. But the thing that shaped Wheeler's physics more than any equation was a piece of mail. His younger brother, Joe, was fighting in northern Italy. Joe had a PhD in American history, a wife, and an infant daughter. He was not a physicist, but he knew what his brother was building at Hanford. And in the late summer of 1944, John received a postcard from Joe bearing 2 words: "Hurry up." Joe knew that whatever was being assembled in the Pacific Northwest could end the war. He was asking his brother to move faster, and John Wheeler could not move fast enough. In October of 1944, Joe Wheeler was shot in a foxhole on a hillside near Florence, Italy. He bled to death. He was in his 20s. His daughter Mary Jo, that infant, later married the physicist James Hartle. Wheeler wrote about this for the rest of his life. One cannot escape the conclusion that an atomic bomb program started a year earlier and concluded a year sooner would have spared 15 million lives, he said. My brother Joe's among them. His own daughter recalled that as he got older, their father wept often over this brother. And if you read Wheeler's journal entries from the 1950s through the 1980s, you can watch a private grief slowly transform into a physics question. The question is not sentimental, it is precise. Does the past exist as a fixed, objective fact? Or does the way you observe the present determine what actually happened? For most physicists, that question is philosophical decoration. For Wheeler, it was personal. Because if the past is fixed, then Joe Wheeler died in a specific, permanent, unalterable way in 1944, and nothing that happens afterward can change that. But if the past depends on how it is observed, then the relationship between Joe's death and John's work, and the bomb and the war and the timeline, is not a settled record. It is something more fluid, something that the future still has a say in. Wheeler did not frame it this way in his papers, because physicists do not write about their brothers in physical review. But the obsession is visible in the work. In 1978, he proposed what he called the delayed choice experiment, and it is one of the most unsettling thought experiments in the history of physics, not because of what it says about photons, but because of what it says about time. Here is the setup. A single photon enters a Mach-Zehnder interferometer. It hits a beam splitter, which gives it 2 possible paths. At the far end, there may or may not be a second beam splitter. If the second beam splitter is in place, the 2 paths recombine, and you see interference, which means the photon traveled both paths simultaneously. If the second beam splitter is removed, you see which path the photon took, which means it traveled one path as a particle. Standard quantum mechanics so far. But Wheeler's twist was that you decide whether to insert or remove that second beam splitter after the photon has already entered the interferometer and passed the first beam splitter. Think about what that means. The photon has already decided whether to be a wave or a particle. It has already committed to one path or both paths. And then you, in the future, change the experimental setup, and the photon's past behavior retroactively conforms to your choice. If you insert the beam splitter, the photon was a wave all along, traveling both paths. If you remove it, the photon was a particle all along, traveling one path. Your future action appears to determine the photon's past. Wheeler pushed this even further with a cosmic version. Imagine a photon emitted by a quasar billions of years ago. It passes a massive galaxy that acts as a gravitational lens, bending its path around both sides of the galaxy. For billions of years, that photon has been traveling through intergalactic space. And now, today, an astronomer on Earth points a telescope and decides how to measure it. If the astronomer measures interference, the photon traveled both paths around the galaxy simultaneously for billions of years. If the astronomer measures which path, the photon traveled one specific path. The astronomer's choice today appears to determine what the photon did billions of years ago. We have to say, Wheeler wrote, that we decide what a photon shall have done after it has done it. This is not fringe. This is not misinterpretation. This is what the math says. The delayed choice experiment was confirmed in the laboratory, first by Carol Alley and colleagues at the University of Maryland in 1986, and most dramatically by a team at the Australian National University in 2007, using a setup closely resembling Wheeler's original proposal. The cosmic version remains a thought experiment, but no physicist disputes that it would produce the predicted results. The equations do not care whether the delay is 8 nanoseconds or 8 billion years. And here is where Marlan Scully enters the story, because Wheeler's experiment raises the question, but it does not answer it. The delayed choice experiment shows that future measurement settings affect what the data looks like, but it does not tell you why. It does not tell you whether the photon's past was genuinely rewritten or whether it never had a definite past to begin with. To get at that, you need a more sophisticated experiment. You need to be able to create witch path information, verify that it destroys interference, and then erase that information and check whether interference comes back. You need, in other words, a quantum eraser. Scully is not the physicist you picture when you think of quantum foundations. He was born on August 3, 1939, in Casper, Wyoming. He is a cattle rancher. He has researched beef cattle production in Wyoming and Mongolia, holds a patent for a time-release medicine bolus for livestock, and has a son who works as a diesel mechanic. He earned his PhD at Yale in 1966 under Willis Lamb, the man whose measurement of the Lamb shift in the hydrogen spectrum helped launch quantum electrodynamics and won him the Nobel Prize in 1955. Scully holds positions at Texas A&M, Princeton, and Baylor. He received the Frederick Ives Medal in 2012, the highest award given by the Optical Society. He has published over 700 papers. The physics community sometimes calls him the quantum cowboy, and it is not entirely a joke. In 1982, Scully and Kai Druhl published a paper in Physical Review A, Volume 25, pages 2208 through 2213, that proposed the quantum eraser. The key insight was that when you perform a double-slit experiment and add a witch path detector, interference disappears. Everyone knew that. The standard explanation, going back to Bohr and Heisenberg, was that the detector physically disturbs the photon, giving it a random momentum kick that washes out the interference pattern. Scully and Druhl showed this explanation was wrong. The interference does not disappear because of a physical disturbance. It disappears because of entanglement. The photon becomes entangled with the witch path detector, and that entanglement, that informational correlation, is what destroys the interference. No kick is needed, no physical disruption at all, just information. And if information is what kills interference, then erasing that information should bring it back. That was the proposal. Tag each photon with witch path information by entangling it with a marker. Verify that interference disappears. Then measure the marker in a way that does not reveal which path the photon took, effectively erasing the information. And check whether the interference pattern re-emerges. It took 18 years to build the experiment that would test this. The experiment that everyone argues about was performed at the University of Maryland, Baltimore County, in a laboratory run by Yanhua Schiff. Schiff had founded UMBC's Quantum Optics Laboratory in 1989 after earning his PhD at the University of Maryland, College Park, and he was already famous in the optics community for a different reason. In 1995, his lab produced the first ghost image, a photograph of the letters UMBC created using photons that had never interacted with the object being imaged. The image was formed entirely through quantum correlations between entangled photon pairs. It should not have been possible, and it was. Schiff won the Willis Lamb Medal in 2002. The lead experimenter was Shih's doctoral student Yoon-ho Kim. Kim would finish his PhD at UMBC in 2001, go on to an Oak Ridge National Laboratory Wigner Fellowship, and eventually become a professor at Postec in South Korea, where he won the Korea Science Award in 2200 and became an Optica Fellow in 2002. But in 1990, he was a graduate student building one of the most debated experiments in modern physics on an optical bench in Baltimore. The paper was submitted to Physical Review Letters in March of 1999 and published on January 3, 2000, as the very first paper of the new millennium. Volume 84, Issue 1 through 5. The authors were Kim, Rong Yu, Sergei Kulik, Yanhua Shih, and Marlan Scully. It occupies a peculiar position in the literature. It has been cited thousands of times and discussed in hundreds of YouTube videos, but the majority of those discussions get at least one important detail wrong, and almost none of them discuss what the paper actually implies about subsequent experiments. Here is how the apparatus worked. A 351.1 nanometer argon ion laser beam hit a double slit. Behind each slit sat a beta-barium borate crystal, or BBO, cut for type 2 spontaneous parametric down conversion. Each pump photon entering a BBO crystal spontaneously split into two daughter photons, each with a wavelength of 702.2 nanometers, exactly double the pump wavelength. These daughter photons were entangled. One was called the signal photon, the other the idler photon. The critical fact is that the signal and idler emerged from specific regions of the crystal corresponding to specific slits, labeled region A and region B, separated by about 0.7 millimeters. A Glan-Thompson prism separated the signal from the idler based on their orthogonal polarizations. The signal photon passed through a lens and traveled to detector D0, which was mounted on a step motor that could scan it across the x-axis, mapping out whatever pattern the signal photons formed. The idler photon entered a small interferometer made of prisms, beam splitters, and mirrors, eventually reaching one of four detectors, D1, D2, D3, or D4. Now here is the part that makes this experiment different from a standard quantum eraser. The optical path from the BBO crystal to the signal detector, D0, was 2.5 meters shorter than the path from the crystal to any of the idler detectors. The signal photon arrived at D0 approximately 8 nanoseconds before its entangled partner reached the idler side detectors. The detectors had a response time of about 1 nanosecond, so this was not a subtle timing difference. The signal photon was unambiguously recorded first. Whatever choice the idler photon made at the beam splitters happened firmly in the future of the signal photon's detection. The four idler detectors were arranged so that D3 and D4 each received idler photons whose path through the interferometer preserved which slit information. If your idler hit D3, it came through slit A. If it hit D4, it came through slit B. These were the witch path detectors. D1 and D2, on the other hand, received idler photons that had been recombined at a final beam splitter in a way that made it impossible to determine which slit they came from. The witch path information had been erased. These were the eraser detectors. And here is what they found. When you looked at all the signal photons arriving at D0 without sorting them, you saw no interference pattern, just a smooth, featureless blob. This is exactly what you would expect if witch path information existed somewhere in the system, because entanglement with the idler photon had effectively tagged each signal photon with a slit label. But when you sorted the D0 data based on which idler detector had fired, the picture changed completely. Signal photons whose idler partners hit D1, the eraser detector, formed a clean double-slit interference pattern. Signal photons whose idler partners hit D2, the other eraser detector, also formed an interference pattern, but shifted by half a wavelength, the complementary antifringe, and signal photons whose idler partners hit D3 or D4, the witch path detectors, formed smooth, single-peaked distributions with no interference at all. The interference patterns and anti-fringes from D1 and D2 added up to exactly the featureless blob you saw in the unsorted data. They cancelled each other out perfectly, which means that looking at D0 alone, you could never tell whether erasure had happened. The information about whether the idler's witch path information had been erased or preserved was invisible at the signal detector until you checked the coincidence records. This is the fact that both sides of the debate seize on, and this is the fact that both sides get partially wrong. The retrocausality enthusiasts are wrong to claim this experiment proves the future sends signals to the past. It does not. No one looking only at D0 can determine whether erasure occurred. The no signaling theorem holds you cannot use this setup to transmit a message backwards in time, period. But the debunkers are wrong too, and their error is more subtle and more consequential. The standard debunking says the interference patterns were always there in the data, hidden in the correlations, and post-selection merely reveals them. Nothing travels backward. The past was not changed. The correlations were established at the moment of entanglement, and the later measurements simply sort the data in a way that makes pre-existing subsets visible. That explanation is correct as far as it goes, but it does not go far enough, because here is the question it fails to answer. What determines which subset a particular signal photon belongs to? The signal photon arrives at D08 nanoseconds before the idler photon reaches any detector. At the moment of the signal photon's detection, the idler photon has not yet encountered the beam splitters that will determine whether witch path information is erased or preserved. The subset that the signal photon belongs to, the one that shows interference versus the one that does not, is determined by an event that has not happened yet. The debunkers will tell you that this is fine because the subsets are defined retrospectively and no individual signal photon carries any mark of which subset it will end up in. And that is true. But it means something that the debunkers rarely say out loud. It means that the individual signal photon at D0 does not have a definite past at the moment of its detection. It does not belong to the interference subset or the non-interference subset. It belongs to neither, or both, or the question is meaningless until the idler measurement is made 8 nanoseconds later. The past of that photon is not determined by what happened to it. It is determined by what will happen to its entangled partner. Now, you can interpret this in multiple ways, and the mainstream physics community has strong opinions about which interpretations are acceptable and which are not. But before we get to those interpretations, you need to understand something that almost nobody outside of the specialist literature knows. The Kim-Shih experiment is not the end of the quantum eraser story. It is the beginning, and what came after it is far more disturbing than what it showed. The standard debunking of the quantum eraser rests on a framework called the no signaling theorem, and within that framework, it is airtight. You cannot use the delayed choice quantum eraser to send a message backward in time. The interference patterns at D0 are invisible without the coincidence data from the idler detectors, and that coincidence data can only be compared with the signal data after the fact through a classical communication channel that travels forward in time at or below the speed of light. Causality, in the communication sense, is preserved. Sean Carroll, in a 2019 analysis originally drafted for his book Something Deeply Hidden, put it as directly as anyone has. The photon does not make a choice to travel through one slit or the other. Its wave function evolves according to the Schrödinger equation, and there is nothing mysterious about post-selection revealing correlations that were established at the moment of entanglement. Carroll is right about the communication constraint. Sabine Hossenfelder is right about the no-signaling theorem. Johannes Fankhauser, in a 2019 paper in Quantum magazine's journal, showed formally that the delayed choice quantum eraser maps onto a standard Bell-type scenario where no temporal weirdness is required to explain the results. And Lorenzo Catani, with colleagues at the Perimeter Institute, demonstrated in Quantum Journal in 2023, Volume 7, Paper 1119, that a classical model with restricted knowledge can reproduce the eraser correlations. Unlike Bell inequality violations, which no classical model can replicate, the quantum eraser's results are, in a precise technical sense, not uniquely quantum. That should settle it, and for the mainstream physics community, it does. The delayed choice quantum eraser is not evidence for retrocausality. Case closed. Move on. But here is what the case closers are not telling you. The no-signaling theorem is a constraint on communication. It is not a constraint on ontology. It tells you what you cannot do with the quantum eraser. It does not tell you what the quantum eraser means, and the distinction between those two things is not a philosophical nicety. It is the crack through which the deepest questions about time and reality escape. Consider what the debunking actually requires you to believe. At the moment, the signal photon hits D0. It does not have a definite history. It is not an interference photon or a non-interference photon. That property is undefined. It will be defined 8 nanoseconds later, retroactively, by the idler measurement. The debunkers are comfortable with this because they frame it as a statement about knowledge, not about reality. We do not know which subset the photon belongs to until we check the coincidence records. The photon itself does not change. Our information about it changes. But that framing smuggles in an assumption that is anything but innocent. It assumes that the photon's history is either definite and unknown, like a coin under a cup, or genuinely indefinite, like a quantum superposition. If it is definite and unknown, then the photon always belonged to one specific subset and we just did not know which one until later. That is a perfectly ordinary classical explanation, but it requires hidden variables, a definite underlying reality that determines the photon's behavior regardless of what measurements are made. And Bell's theorem, confirmed in loophole-free experiments by Henson and colleagues in 2015, tells you that local hidden variables cannot reproduce quantum predictions. So if the photon's history is definite, the hidden variables must be non-local. Something somewhere is influencing that photon's history from a distance, instantaneously. And if the photon's history is genuinely indefinite, if it literally does not have a past until the idler measurement defines one, then you have a different problem. You have a universe in which the past is not fixed, in which events that have already been recorded at a detector do not have definite properties until a future measurement assigns them. That is not retrocausality in the signal-sending sense, but it is something arguably stranger. It is a universe where the past is under construction, perpetually, and the construction crew is working from the future. The mainstream response to this is to shrug. Quantum mechanics is weird. Complementarity handles it. Do not ask what the photon really did between the source and the detector. The question is not well defined, and within the Copenhagen interpretation, that response is internally consistent. But it is a refusal to answer the question, not an answer to it. And there is a growing community of physicists who think the question deserves better. This community has a history that begins with suppression. In 1947, a French physicist named Olivier Costa de Beauregard was working under Louis de Broglie in Paris. Costa de Beauregard had been studying the EPR paradox, Einstein's famous argument that quantum mechanics must be incomplete because it seemed to require instantaneous action at a distance. And he had an idea. What if the two distant particles in the EPR experiment were not communicating instantaneously across space, What if they were communicating through time? Specifically, he proposed that correlations between entangled particles could be explained by a zigzag path through space-time, a retarded wave traveling forward in time from the source to one particle, and an advanced wave traveling backward in time from one measurement to the source and then forward again to the other particle. No faster than light communication required, no violation of special relativity, just causation that runs in both temporal directions along ordinary time-like paths. De Broglie forbade him from publishing. That is not a metaphor. De Broglie literally prohibited his student from submitting the paper. It was too radical, too incompatible with the Copenhagen framework that dominated post-war physics. Costa de Beauregard waited. It was not until Feynman published his diagrams in 1948, depicting positrons as electrons traveling backward in time, that backward-in-time physics acquired even a shred of respectability. De Broglie finally relented, and Costa de Beauregard published a version of his proposal in Comptes Rendus in 1953. The paper made almost no impact. The Copenhagen interpretation was too entrenched, and the idea that causation could flow backward was too disturbing for a physics community that was busy winning the Cold War with quantum electrodynamics. But the idea did not die. It went underground, and it resurfaced in 3 distinct lines of work that, taken together, constitute what is now a serious research program, one that mainstream physics has largely ignored. The first line comes from Yakir Aharonov, one of the most important living physicists, a man who has arguably done more to expose the strangeness of quantum mechanics than anyone since Bell. In 1964, Aharonov, along with Peter Bergman and Joel Lebowitz, published a paper in Physical Review, volume 130-4, page B1410, that introduced what is now called the two-state vector formalism. The idea is deceptively simple. Standard quantum mechanics describes a system at any given moment using a single quantum state, the ket, which evolves forward in time from its preparation. Aharonov proposed that a complete description requires 2 states. The first is the usual forward evolving state from past preparation. The second is a backward evolving state from future measurement. The system at any moment is described by both. Together, they form the two-state vector. This formalism is not speculative. It is empirically equivalent to standard quantum mechanics. It makes all the same predictions. But it naturally accommodates something that standard quantum mechanics does not. Backward in time influences. In the two-state vector picture, the outcome of a measurement at time t depends not just on what happened before t, but on what will happen after t. The future measurement setting is literally part of the description of the system at the present moment. In 1988, Aharonov, David Albert, and Lev Weidman pushed this further with a paper in Physical Review Letters, volume 60, pages 1351 through 1354, introducing weak measurements. They showed that if you make a very gentle measurement of a quantum system, so gentle that it barely disturbs the state, you can obtain something called a weak value. Weak values can lie outside the normal range of eigenvalues. A spin half particle can have a weak value of spin equal to 100. This sounds impossible, and when the paper was first published, many physicists assumed it was wrong. It was not wrong. Weak values have been confirmed in dozens of experiments and are now a standard tool in quantum optics laboratories worldwide. And they only make physical sense within the two-state vector formalism, where the future measurement is part of the story. The second line of work comes from Hugh Price, now Emeritus Bertrand Russell Professor of Philosophy at Cambridge. Price is a philosopher, not a physicist. And that matters because it means he approaches the foundations of physics without the professional incentives to leave certain questions unasked. His 1996 book, Time's Arrow and Archimedes' Point, published by Oxford University Press, made an argument that physicists found either liberating or infuriating depending on their temperament. The fundamental laws of physics are time-symmetric. Run them forward or backward, they work the same way. Every physicist agrees on this. But when those same physicists explain why quantum measurements produce definite outcomes, or why entangled particles are correlated, they invariably invoke processes that run in only one temporal direction. They assume, without justification, that causes precede effects. Price called this the double standard fallacy. You cannot accept time-symmetric laws and then smuggle in time-asymmetric explanations without admitting you have added something that the laws themselves do not contain. Price formalized this into what he calls the time-symmetric retrocausality argument. If you assume that the quantum state is real, that the laws are time-symmetric, and that measurement involves a discrete change, then retrocausality follows. You do not get to choose. It is a logical consequence. In 2017, Matthew Leifer and Matthew Pusey, in a paper published in Proceedings of the Royal Society A, Volume 473, Paper 2016-06-07, strengthened this result. They showed that even if you drop the assumption that the quantum state is real, time symmetry plus a reasonable mediation condition still implies retrocausality. The paper was published in one of the oldest and most respected scientific journals in the world. It accumulated a modest number of citations. Most working physicists have never read it. The third line comes from Ken Wharton, a professor at San Jose State University who earned his PhD from UCLA in 1998. Wharton's approach is the most radical of the three, and arguably the most elegant. He argues that the universe does not compute itself forward in time, step by step, like a simulation running on a clock. Instead, it solves boundary value problems, like Fermat's principle for light. When light travels between 2 points, it takes the path that minimizes travel time, but it does not know in advance which path that is. The path is determined by both the starting point and the ending point simultaneously. The math works the same way as classical action principles in Lagrangian mechanics, and those principles have been the foundation of physics since the 18th century. Wharton applies this to quantum mechanics. Bell correlations between entangled particles, the correlations that no local hidden variable model can reproduce, can be explained through what he and Price call constrained collider models. The idea uses Bergson's bias, a well-known statistical phenomenon where conditioning on a common effect creates a spurious correlation between its causes. In Wharton's framework, the common effect is the future boundary condition. Past and future are both inputs to the physics, and the apparent non-locality of quantum mechanics is actually an artifact of looking at a four-dimensional boundary value problem through the lens of step-by-step temporal evolution. In 2020, Wharton and Nathan Argerman published a comprehensive review in Reviews of Modern Physics, Volume 92, Paper 021-002. Reviews of Modern Physics is the most prestigious review journal in all of physics. The paper coined the term future input dependence as a precise replacement for retrocausality, deliberately choosing a phrase that sounds less like science fiction and more like what it actually is. Physics where the future boundary condition matters. The paper surveyed at least 7 distinct retrocausal models, showed that they are internally consistent, and argued that retrocausality is the most conservative resolution of Bell's theorem because it preserves both locality and realism. The two things that Bell's theorem seems to forbid simultaneously can be saved if you allow the future to influence the past. And then there is Rod Sutherland at the University of Sydney, who built the most explicit retrocausal model of all. His 2008 paper in Studies in History and Philosophy of Modern Physics, Volume 39, pages 782 through 805, presented the causally symmetric Bohm model. Standard Bohmian mechanics gives particles definite positions and velocities at all times. guided by a pilot wave. It is deterministic. It reproduces all quantum predictions, but it is explicitly non-local. Sutherland's modification adds a second ingredient, a final wave function, determined by future measurement settings. Each particle gets a complete description from both past preparation and future measurement. Bell correlations arise through Costa de Beauregard's zigzag, causal influence traveling forward from the source to one detector, backward in time to the source, and then forward again to the other detector, all along time-like trajectories, no faster than light influence, no preferred reference frame, natural Lorentz invariance, which standard Bohmian mechanics lacks and has always been embarrassed about. Sutherland called retrocausality the most conservative option available because it preserves the most essential features of our existing theories. Wharton and Price, writing in The Conversation in 2023, noted that there is now a thriving group of scholars working on quantum retrocausality, but they added a caveat that tells you everything about where this field stands. The field is still invisible to some experts in the wider field. It keeps getting confused with a different proposal called superdeterminism, which is not at all the same thing. Superdeterminism says that measurement choices and hidden variables were correlated by a common cause in the distant past, essentially a cosmic conspiracy that undermines the entire basis of experimental science. Retrocausality says that measurement choices causally influence particle properties backward in time. One destroys free will, the other preserves it. The fact that mainstream physicists routinely conflate them suggests that the mainstream has not seriously engaged with the retrocausality literature. And here is where the story takes its most unsettling turn. Because everything I have told you so far is about the standard quantum eraser, the experiment that Kim-Shih and Scully published in 2000. The retrocausality debate, the interpretation wars, the growing underground of time-symmetric models, all of that is about what happens when you erase which path information once. But what happens when you erase it, then restore it, and then erase it again? This is the question that takes us beyond what any YouTube video has covered, into a corner of the physics literature where the papers have single-digit citation counts, where results were announced and then abandoned, and where the absence of an obvious experiment is so conspicuous that it starts to look less like an oversight and more like a choice. Because the quantum eraser has extensions, real, published, peer-reviewed extensions that push the concept beyond anything the standard debunking addresses. And the implications of those extensions have, as far as I can tell, never been discussed publicly. The first and most important extension was published in 1999, the same year the Kim-Shih experiment was being assembled in Baltimore. Robert Garisto at Brookhaven National Laboratory and Lucian Hardy, then at Oxford, published a paper in Physical Review A, Volume 60, page 827, with a title that sounds technical but hides something extraordinary: Entanglement of Projection and a New Class of Quantum Erasers. What Garisto and Hardy showed was that the quantum eraser does not just restore interference, it can restore entanglement itself. Think about what that means. In the standard quantum eraser, you start with two entangled photons. You tag one with which path information, which destroys the interference pattern, then you erase the tag and interference comes back. The entanglement between the signal and idler photons is the mechanism that makes all of this possible, but the entanglement itself is treated as a fixed background resource. Garisto and Hardy showed that this picture is incomplete. They demonstrated, theoretically, that when you perform a projective measurement on one member of an entangled pair, you can disentangle them, creating a separable state where no quantum correlations remain. The two particles become, in every measurable sense, independent. But then, by performing a specific operation on an auxiliary system, you can restore the entanglement. The particles become correlated again, as if the disentangling measurement had never happened. The implications are staggering if you take them seriously. In the standard quantum eraser, you are restoring a pattern. In the disentanglement eraser, you are restoring a relationship. The connection between two particles, the quantum correlation that Einstein called spooky action at a distance, can be severed and then re-established. It is not permanent, it is not fragile in the way people assume. It is, in a precise technical sense, recoverable, as long as the information about the disentangling measurement remains stored in a quantum system that you can manipulate. This was not just theory. In 2001, Gilles Teclemariam and colleagues published an experimental confirmation in Physical Review Letters, volume 86, page 5845, using nuclear magnetic resonance. They built an NMR analog of the quantum disentanglement eraser and demonstrated that entanglement could indeed be destroyed and then restored through a carefully chosen sequence of operations. The paper's title was NMR Analog of the Quantum Disentanglement Eraser. It exists. It was peer-reviewed. It was published in one of the highest impact physics journals in the world. Try to find a YouTube video about it. Try to find a popular science article. Try to find anyone, anywhere who has discussed the implications of this result. In a public forum, you will not find them. The paper has a respectable number of citations in the specialist literature, but in the ecosystem of science communication, in the world of explainers and debunkers and pop physics channels, it does not exist. And Scully himself pushed further. In 2004, M. Suhail Zuberi, Girish Agarwal, and Marlan Scully published a paper in Physical Review A, Volume 17, Paper 012-316, describing a quantum disentanglement eraser implemented in cavity quantum electrodynamics. This was not an NMR analog. This was a proposal for a full optical implementation using atoms coupled to microwave cavities, the same kind of setup that Serge Haroche used in the work that won him the Nobel Prize in 2012. Zuberi, Agarwal, and Scully showed that a three-level atom passing through two cavities could be disentangled and then re-entangled by manipulating the cavity fields. The key passage in their paper describes successive manipulations of cavity states that cycle the system through states of entanglement and separability. Successive manipulations, cycles of entanglement and separability. This is the language of iterated erasure. Create the correlation, destroy it. Destroy it again, and the theory says there is no limit to how many times you can do this. But there is another paper that goes even further, and this one is almost completely unknown. In 2008, Ramiz-ul-Islam, Ashfaq Koza, Jinhyang Li, and Manzoor Ikram published a paper in the European Physical Journal D, Volume 48, pages 271 through 277, describing what they called a collective disentanglement eraser. Their setup involved two pairs of pre-entangled cavities, 4 cavities total, and a sequence of atoms passing through them. The collective erasure procedure did not merely restore the original entanglement, it extended it. 2 pairs of entangled cavities became a 4-qubit cluster state, a resource for quantum computation that did not exist before the erasure procedure created it. Read that again. The erasure process did not just undo the disentanglement, it produced more entanglement than the system started with. The act of erasing which path information generated quantum correlations that had never existed. The past was not restored. The past was upgraded. This paper has fewer than 15 citations. In the broader conversation about quantum erasers and retrocausality, it is invisible. And then there is a paper that makes the retrocausal implications almost impossible to ignore, published in a venue so obscure that finding it requires a deliberate search through conference proceedings. In 2007, Antonio Bramman, Gianni Garbarino, and Beatrix Heismeyer published a contribution to the Frascati Physics series, volume 43, page 255, with a title that should have made headlines: Erasing the Present, Changing the Past. The paper proposed using neutral kaons, particles that naturally oscillate between matter and antimatter states, as quantum erasers at the KLOE2 detector at the Frascati National Laboratory in Italy. The kaonic system offers something the photonic quantum eraser cannot. Neutral kaons have two decay channels with different lifetimes, the short-lived K-short and the long-lived K-long, and the Witch width. The information about which decay channel the kaon is in serves as a natural Witch path marker, but unlike photonic polarization markers, the kaonic marker evolves dynamically over time. The Witch path information does not just sit there waiting to be erased or preserved. It actively changes as the kaon propagates. Bramman, Garbarino, and Heismeyer showed that both active and passive erasure procedures are possible, and that the temporal structure of the kaonic system means that the past of the kaon pair can be effectively modified by measurements performed at later times. The paper has fewer than 10 citations. The experiment was never performed at KLOE2 or anywhere else. And perhaps most revealingly of all, in 2005, Yakir Aharomov and Suhail Zuberi published a review article in Science, volume 307, pages 875 through 879, titled Time and the Quantum, Erasing the Past and Impacting the Future. This is Science magazine. This is one of the 2 or 3 most widely read scientific journals on Earth. The paper surveyed the quantum eraser and its extensions, discussed the delayed choice experiment, and outlined the implications for the nature of time. And in the references, as reference 19, it cited M. O. Scully, unpublished results in the context of using quantum eraser entanglement for subdiffraction limit microscopy. Unpublished results by the inventor of the quantum eraser, referenced in Science magazine. In 2005, 20 years ago, those results, as far as the public record shows, were never formally published. They exist as a ghost in the citation record, a placeholder for work that was done and then, for whatever reason, never shared with the rest of the field. You need to sit with that for a moment. The man who invented the quantum eraser apparently had further results. These results were considered significant enough to reference in a review article in Science, and they were never published, not retracted, not contradicted, not superseded by better work, just never written up. The data, or the theory, or whatever it was, went into a drawer and stayed there. And this is where the invisible scandal becomes impossible to dismiss as academic carelessness, because the theoretical prediction is not ambiguous. Quantum mechanics says, clearly and without controversy, that which path information can be marked, erased, marked again, and erased again as many times as you want, provided the information stays in a controllable quantum system. Every interpretation agrees on this. Copenhagen agrees, many worlds agrees, Bohmian mechanics agrees, the transactional interpretation agrees, the retrocausal models agree. There is no interpretation of quantum mechanics that predicts the multi-stage eraser would fail. The only requirement is that the Witch path information not leak into the environment through decoherence. As long as you maintain quantum control over the marker, you can cycle it through as many erase and restore operations as your apparatus can handle. Each cycle costs at least kT times the natural logarithm of 2 per bit, which is Landau's principle, the thermodynamic minimum for erasing a bit of information. But there is no quantum mechanical barrier, no principle of physics that says you have used up your erasures, no rule that says the past can only be rewritten once. And yet no one has built this experiment, No one has published data from a multi-stage quantum eraser. The theoretical papers that approach this territory, the doubly tagged erasers and collective disentanglement erasers and chaonic erasers, accumulate citation counts in the single digits and are never followed up with laboratory implementations. The gap between what the theory permits and what the experiments have tested is enormous, and it has been sitting there for over 2 decades. This is not a case where the experiment is prohibitively expensive. It is not a case where the technology does not exist. Cavity QED systems capable of performing the necessary operations have been available since the late 1990s. Ion trap systems, which offer even better quantum control, have been performing far more complex operations for quantum computing applications for years. The multi-stage quantum eraser is, by the standards of modern quantum optics, a relatively straightforward experiment, not easy certainly, but well within the capabilities of any of a dozen laboratories around the world. So why has nobody done it? There are innocent explanations. Maybe the experiment is less interesting than I am making it sound. Maybe the theoretical prediction is so unambiguous that confirming it would not tell us anything new. Maybe the resources are better spent on quantum computing or quantum cryptography or any of the other applied quantum technologies that attract funding. These explanations are plausible and they may be partially true. But there is another explanation that fits the pattern better. The multi-stage quantum eraser would not just confirm a theoretical prediction. It would force the physics community to confront a question it has spent decades avoiding. If the past can be rewritten once, that is strange but manageable. You can tell yourself that the erasure is just post-selection, just an artifact of how information is structured in quantum mechanics. You can live with one rewrite. But if the past can be rewritten 10 times, 50 times, 100 times, each rewrite changing what the signal photon's data means when you sort it, each cycle demonstrating that the fact of what the photon did at the double slit is a function of an arbitrarily long chain of future measurements, then the word past loses its meaning. It is no longer something that happened. It is something that is happening continuously. Right now, and every measurement that will ever be made in the future has the potential to revise it again. The retrocausality camp would see this as vindication. The debunking camp would have to develop a much more sophisticated account of what post-selection means when the selection can be iterated indefinitely. And the broader physics community would have to face the fact that the most basic question about the nature of time, the question that began with a postcard from a foxhole in Italy, has a possible experimental answer that nobody wanted to find. That is not a scientific failure. That is something closer to a collective flinch. The experiment that could probe the deepest question about the past was available, was partially explored in scattered and forgotten papers, and was never completed. Not because it could not be done, because the answer, whatever it turned out to be, would be too difficult to live with. And this takes us to the theoretical framework that makes the whole thing so disturbing. Because the retrocausal models do not just predict that the multi-stage eraser would work, they predict something specific about what iterated erasure would reveal about the structure of time itself. Start with Aharonov's two-state vector formalism. In this picture, every quantum system at every moment is described by two states, one propagating forward from its past preparation, one propagating backward from its future measurement. The system does not just have a history, it has a destiny, and both of them together determine what the system is doing at the present moment. In a standard quantum eraser, the forward evolving state carries the initial superposition from the double slit, and the backward evolving state carries the constraint imposed by the idler measurement. When the idler is measured at an eraser detector, the backward state propagates back through time and selects a subset of signal photon events that show interference. When the idler is measured at a Witch path detector, a different backward state selects a subset that does not. Now imagine the multi-stage eraser in this formalism. The signal photon arrives at D0. Its forward evolving state is set by the double slit. Its backward evolving state is set by the final measurement of the idler, which has not happened yet. But before that final measurement, the idler passes through a sequence of operations: erase, restore, erase, restore. Each operation changes the basis in which the idler will eventually be measured. And each basis change alters the backward evolving state that propagates back to the signal photon. In the two-state vector picture, every intermediate operation in the erasure chain sends a new backward state rippling through the system's past. The signal photon at D0 is not receiving one message from the future. It is receiving a sequence of messages, each one overwriting the last. The photon's history is not rewritten once. It is rewritten with every cycle of the eraser. And because the two-state vector formalism is empirically equivalent to standard quantum mechanics, this is not a speculative interpretation. It is a mathematically rigorous description of what the equations say. Wharton's Lagrangian picture makes this even more vivid. In his framework, the physics of the entangled system is not computed forward step by step, but solved all at once as a four-dimensional boundary value problem. The initial conditions at the double slit and the final conditions at the idler detectors jointly determine the entire history. Change the final conditions and you change the solution everywhere. The multi-stage eraser in this picture is like a novel being rewritten from the ending backward. Change the last chapter and the earlier chapters restructure themselves to maintain consistency. The past does not resist revision. It cooperates with it. And Sutherland's causally symmetric Bohm model gives the most explicit picture of all. In his framework, each particle has a definite trajectory through space-time, guided by both a forward pilot wave from past preparation and a backward pilot wave from future measurement. The zigzag of causal influence, the Costa de Beauregard path from source to detector to source to detector, is not a metaphor. It is the literal causal structure. In the multi-stage eraser, each cycle of erasure and restoration would send a new backward pilot wave through the system, altering the effective guidance of the signal photon. The photon's trajectory would be, in principle, a function of every future measurement in the chain, not just the last one. This is worth pausing over, because the implications are not limited to photons on an optical bench. If these models are correct, and they are internally consistent and empirically indistinguishable from standard quantum mechanics, then the same logic applies everywhere. Every quantum system in the universe is described by both its past and its future. Every particle carries information not just about where it came from, but about where it is going. And every measurement, everywhere, retroactively constrains the histories of every particle it is entangled with. The block universe, the picture of space-time that Einstein's relativity strongly suggests, is usually described as a four-dimensional block in which past, present, and future all coexist. Physicists often describe it as a frozen sculpture. Nothing moves. Nothing changes. The entire history of the cosmos is laid out like a film strip, and what we experience as the flow of time is an illusion created by the way our consciousness threads through the block. But the retrocausal models say the block is not frozen. It is not a sculpture. It is something more like a self-consistent solution to a system of equations with boundary conditions at both the beginning and the end of time. The past and the future constrain each other reciprocally, and what we call history is the solution that satisfies all the constraints simultaneously. Change a measurement in the future and the solution adjusts, not just in the future, but everywhere. Wheeler had a phrase for this. He called the universe a self-excited circuit. He first used the term in a lecture at the Santa Fe Institute in 1989, and he drew a famous diagram to illustrate it, a capital U with an I at one end, bending back to look at itself. The universe brings itself into existence through observation, not in a mystical sense. In the precise sense that the quantum state of the universe depends on what measurements are performed within it, and those measurements are performed by systems, including us, that the universe itself produced. This is usually treated as philosophy, as a provocative metaphor, as the kind of thing an aging physicist says at the end of a long career when he has earned the right to speculate. But Aharonov's formalism and Wharton's Lagrangian models and Sutherland's causally symmetric Bohmian mechanics give Wheeler's self-excited circuit a mathematical backbone. The universe is a self-consistent solution to a boundary value problem. The boundary conditions include the future. The future constrains the past. Observation does not merely reveal reality, it participates in constructing it. And the multi-stage quantum eraser is the experiment that could test this. Not by proving retrocausality in the signal-sending sense, because the no-signaling theorem would still hold, and the interference patterns would still be invisible without post-selection, but by demonstrating that the number of times the past can be rewritten through iterated erasure has no limit. By showing that the signal photon's data can be sorted into interference or non-interference an arbitrary number of times depending on an arbitrarily long chain of future measurements. By forcing the debunkers to explain what post-selection means when the selection procedure can be repeated indefinitely, each cycle yielding a different pattern, each cycle demonstrating that the signal photon's past has no fixed character until the last measurement in the chain is made. If the experiment works, and quantum mechanics unambiguously says it will, then the word past needs to be redefined. What you call your past is not a sequence of events that happened, it is a set of correlations waiting to be sorted. And the sorting has not been completed yet. And it may never be completed because every future measurement has the power to resort everything that came before it. That idea is either the most important insight in the history of physics or the most terrifying. And the fact that the experiment that could demonstrate it, an experiment within reach of current technology, has never been performed, tells you something about which possibility the physics community is more afraid of. But the story does not end with what has not been done, because there are clues in the experiments that have been done, clues that point towards something even more disturbing than iterated erasure, something about the nature of information itself, and about the relationship between what is known and what is real, that the standard interpretations of quantum mechanics were specifically designed to avoid confronting. Consider an experiment that has nothing to do with erasure, at least on the surface, but that reveals the same underlying truth from a completely different angle. In 1993, Avshalom Elitzur and Lev Weidman, both at Tel Aviv University, published a paper in Foundations of Physics, volume 20-3, pages 987 through 997, proposing what they called interaction-free measurement. The physics community came to know it as the bomb tester, and the name is not a joke. It is a literal description of the thought experiment, and it is one of the strangest results in quantum mechanics. The setup is a Mach-Zehnder interferometer, the same basic apparatus Wheeler used for his delayed choice experiment. A single photon enters through a beam splitter, which sends it along two possible paths. The paths recombine at a second beam splitter, and the interferometer is carefully balanced so that destructive interference occurs at one of the two output ports. Call the output with destructive interference the dark port. In a properly balanced interferometer, no photon ever exits the dark port. Every photon exits the other port, the bright port. This is a straightforward consequence of wave interference, and it has been verified in countless experiments. Now place an object in one of the two paths. Elitzur and Weidman imagined a bomb with a single photon-sensitive trigger. If the photon travels along the path with the bomb explodes. If the photon travels along the other path, nothing happens. The question they asked was deceptively simple. Can you determine that the bomb is live without detonating it? Classical physics says no. To learn whether the bomb is there, you have to send something along that path, and if the bomb is there, it explodes. There is no way around it. Information requires interaction. Quantum mechanics says otherwise. When the bomb is placed in one path, it acts as a which path detector. Its mere presence, its capacity to absorb the photon, collapses the superposition. The photon can no longer travel both paths simultaneously because one of the paths would trigger a macroscopic, irreversible event. And when the superposition collapses, the destructive interference at the dark port is destroyed. The dark port is no longer dark. Here is what happens in practice. You send a photon into the interferometer with the bomb in one arm. There are three possible outcomes. In roughly 50% of trials, the photon takes the path with the bomb, and the bomb explodes. You have learned the bomb is live, but at the cost of destroying it. In roughly 25% of trials, the photon exits the bright port. You learn nothing, because the bright port fires regardless of whether the bomb is present. But in the remaining 25% of trials, something remarkable occurs. The photon exits the dark port, the port that should be permanently dark if both paths are open, the port that only fires when something has blocked one of the paths. The photon exits the dark port, certifying that the bomb is live without ever having traveled along the path where the bomb sits. The photon did not interact with the bomb. The bomb did not explode, and yet you now know with certainty that it is there and it is functional. This is interaction-free measurement. You have obtained information about an object without any physical interaction between the object and the measuring device. The photon that exited the dark port never touched the bomb. It traveled along the other path entirely. But the possibility that it could have taken the bomb path, the counterfactual that did not occur, was enough to collapse the superposition and change the interference pattern at the output. The original Elitzer-Vaidman scheme had a 25% efficiency, which is not great if you are a bomb disposal technician. But in 1999, Paul Kwiat, Harold Weinfurter, and Anton Zeilinger, the latter of whom would win the Nobel Prize in 2022 for his work on entanglement, published a dramatic improvement in Physical Review Letters, Volume 83, page 4725. They used the quantum Zeno effect, the same phenomenon that Faultlines covered in a previous video, to cycle the photon through the interferometer n times, with small polarization rotations at each pass. Each cycle gives the bomb a chance to absorb the photon, but because the rotation is small, the probability of absorption per cycle is tiny. And here is the Zeno trick. Repeated observation suppresses transitions. The more frequently you check whether the photon has been absorbed, the less likely the absorption becomes. In the limit of large n, the explosion probability drops as roughly 1/n. The detection efficiency approaches 100%. You can certify the bomb is live with near certainty while having an arbitrarily small probability of triggering it. Kwiat and colleagues demonstrated experimental efficiencies exceeding 73% and showed that 85% was feasible with their apparatus. In principle, a sufficiently patient experimentalist could detect the bomb with 99.9% certainty while having a 1 in 1,000 chance of detonation. Information about the bomb obtained without interacting with it. Knowledge extracted from an event that did not happen. Now think about what this shares with the quantum eraser, because the connection is not obvious, but it is deep. In the bomb tester, the photon that exits the dark port traveled a path that never encountered the bomb, but the existence of the bomb on the other path changed what the photon did. The counterfactual matters. In the quantum eraser, the signal photon is detected at d0 before the idler photon reaches any detector. But the future measurement of the idler changes what the signal photon's data means when sorted. The future matters. In both cases, something that did not happen, an interaction that did not occur in one case, a measurement that has not been made yet in the other, determines the outcome. The physics community treats these as separate phenomena. The bomb tester is filed under interaction-free measurement. The quantum eraser is filed under complementarity and entanglement. They appear in different textbook chapters and different review articles, but they are both manifestations of the same principle. The universe does not track only what happened. It tracks what could have happened. And the full set of possibilities, including the ones that were never actualized, determines the results. This principle has a name, though it is rarely used outside the Foundation's community. It is called counterfactual definiteness, and its violation is one of the most troubling features of quantum mechanics. In classical physics, you can always say what would have happened if you had made a different measurement. The coin was heads before you looked. The ball was in the box before you opened it. The world has a definite state at all times, and your measurements reveal that state without creating it. In quantum mechanics, you cannot say this: the property you did not measure does not have a definite value. And the properties you did measure may depend on the properties you chose not to measure. The counterfactual is not a harmless what-if. It is part of the physics. This is actually what Bell's theorem proves, though it is rarely framed this way. Bell showed in 1964 that no theory satisfying three assumptions simultaneously can reproduce the predictions of quantum mechanics. Those assumptions are locality, which says distant events cannot instantly influence each other; realism, which says particles have definite properties whether or not you measure them; and what is sometimes called measurement independence, which says your choice of what to measure is not correlated with the hidden properties of the particles. Violate any one of the three and you can reproduce the quantum predictions. The mainstream reaction to Bell has been to abandon realism, to say that particles simply do not have definite properties until measured. That is the Copenhagen response. Many worlds abandons the idea of single outcomes. Bohmian mechanics abandons locality. And the Retrocausality program abandons measurement independence, but in a very specific way. It says that your measurement choice is correlated with the hidden properties not because of a cosmic conspiracy in the past, but because your future measurement reaches backward and sets those properties. The correlation runs through time, not around it. This is the fork in the road that the multi-stage eraser would illuminate, because if you perform 10 cycles of erasure and restoration, and the signal photon's data obediently sorts into interference or non-interference, depending on the final cycle, then measurement independence is violated in the most dramatic way imaginable. The signal photon's behavior is correlated with a measurement choice that was made 10 operations after its detection, and those 10 operations could have gone differently at every step. The correlation is not with a single future event, but with an entire chain of future events. And the length of the chain is arbitrary. The debunker can still say post-selection. The debunker can always say post-selection. But at some point, post-selection becomes a word that is doing the work of a theory without actually being one. It describes what you do with the data. It does not explain why the data has the structure it has. And when the post-selection criterion is a chain of 10 operations on a photon stored in a quantum memory, each operation chosen freely by the experimenter, the word post-selection starts to buckle under the weight of what it is being asked to carry. The bomb tester makes this visceral. A photon that never touched the bomb knows the bomb is there. The quantum eraser makes it temporal. A photon that was detected before the erasure decision knows whether erasure will occur. And the disentanglement eraser makes it structural. A relationship between particles that was severed knows it can be restored. And the mathematics that describes the severed state is different from the mathematics that describes a state where the relationship never existed. Put all three together, and you get a picture of reality that is profoundly different from the one you learnt in school. Reality is not a sequence of events that occur in order, each one determining the next. Reality is a web of relationships between possible events, actual events, and future events, all of which constrain each other simultaneously. The past constrains the future, yes, but the future constrains the past with equal mathematical authority. And the counterfactual, the road not taken, constrains everything. This is what makes the absence of the multi-stage quantum eraser so conspicuous. Because if you combine the quantum eraser with the bomb tester's lesson about counterfactuals, you get something that no existing experiment has probed. In a multi-stage eraser, each cycle of erasure and restoration is not just changing what the signal photon's data means, it is changing the counterfactual structure of the experiment. At each stage, the set of what could have happened is different because the erasure operation changes which measurements were possible and which were not. And if counterfactuals matter, if the universe really does track the roads not taken, then each cycle of the multi-stage eraser is not just rewriting the past, it is rewriting the set of possible pasts. It is not editing a document, it is editing the set of documents that could have been written. That distinction is important, and nobody has tested it experimentally, and the reason nobody has tested it may be that nobody wants to know the answer. Let me be precise about what the multi-stage eraser would involve, because the vagueness of the theoretical discussion is part of why this experiment has been easy to ignore. The details matter. You begin with the standard delayed choice quantum eraser apparatus, a pump laser, a double slit, a BBO crystal producing entangled photon pairs, a signal detector, and a set of idler detectors. The signal photon is detected first. The idler photon enters the interferometer. So far, everything is identical to the Kim-Shih experiment. But instead of sending the idler directly to the beam splitters and detectors, you insert additional optical elements in the idler's path. Specifically, you add a controllable quantum memory, a device that can store the idler photon's quantum state, hold it for a chosen duration, and then release it. Quantum memories based on atomic ensembles, rare earth-doped crystals, and single-trapped atoms have been demonstrated with storage times ranging from microseconds to minutes. The technology exists. The protocol proceeds in stages. In stage 1, the idler enters the quantum memory and its which path information is stored. At this point, if you were to release the idler and send it to the which path detectors, you would see no interference in the signal data. The which path information exists. The past is tagged. In stage 2, you perform an erasure operation on the stored idler. This could be a basis rotation, a quantum gate that transforms the which path basis into a superposition basis, effectively erasing the slit label. If you release the idler now and sent it to the eraser detectors, the signal data would show interference when sorted by coincidence. The past has been untagged. The tag has been erased. In stage 3, you perform the inverse operation. You rotate the idler back into the which path basis. The slit label is restored. The information that was erased now exists again. If you measured now, the signal data would show no interference. The past has been retagged. In stage 4, you erase again. Interference returns. Stage 5, you restore again. And so on, for as many cycles as your quantum memory's coherence time allows. At the end of the sequence, whenever you choose to stop, you release the idler to one of the detectors. If the final operation was an erasure, you send it to the eraser detectors and the signal data shows interference. If the final operation was a restoration, you send it to the which path detectors and the signal data shows no interference. The history of the signal photon, its membership in the interference or non-interference subset, is determined by the last operation in an arbitrarily long chain. Now here is the critical question that the experiment would answer. During the intermediate stages, when the idler is sitting in the quantum memory and the which path information has been alternately erased and restored multiple times, what is the state of the signal photon's data? It was detected long ago, perhaps microseconds ago, in laboratory terms, perhaps much longer if you use a high-performance quantum memory. The electrical signal has been recorded. The data is in a computer file, but that data does not yet have a definite character. It does not belong to the interference subset or the non-interference subset. It will not acquire that character until the final measurement of the idler, which could be seconds, minutes, or in principle hours, in the future. The debunking community will say, this is still just post-selection. The data was always both. You just have not sorted it yet. And in one sense, they are right. But the multi-stage eraser forces a question that the single-stage eraser does not. If the sorting criterion can change an arbitrary number of times before being finalized, and if each change corresponds to a different physical operation on the idler, then what does it mean to say the data was always both? Is the past genuinely indeterminate during those intermediate stages? Or is there a definite fact about the signal photon that persists through the chain of operations, a hidden variable that determines which subset it belongs to regardless of what happens to the idler? If the past is genuinely indeterminate, then the multi-stage eraser demonstrates that the duration of that indeterminacy is not limited to 8 nanoseconds. It can be extended to any timescale. The past remains unfixed for as long as the idler remains in the quantum memory. And if the idler is never measured, if it is lost to decoherence or absorbed by the environment without a controlled measurement, then the signal photon's data never acquires a definite character at all. It remains in the unsorted, featureless blob forever. The past was never written. And if there is a hidden variable, if the signal photon always belonged to one specific subset, then that hidden variable must be correlated with the outcome of a measurement that has not happened yet, and that could go either way depending on an operation performed at an arbitrary time in the future. That hidden variable must, in some sense, know the future. And Bell's theorem tells you that local hidden variables cannot reproduce quantum predictions, so the hidden variable must be non-local or retrocausal, or both. Either way, the multi-stage eraser would produce data that forces a choice between deeply uncomfortable alternatives. The past is genuinely open, with no fixed character, for an arbitrarily long time after the events occurred, or the past is fixed by hidden variables that are sensitive to future measurements. Neither option is compatible with the everyday assumption that the past is determined by the past. This is not speculation. Every interpretation of quantum mechanics agrees that the multi-stage eraser would produce the results I have described. The disagreement is entirely about what those results mean, but the disagreement cannot even begin until the experiment is performed. And the experiment has not been performed. Why not? I have already offered the innocent explanations. The experiment is not easy. Quantum memories are imperfect. Decoherence is always lurking. The theoretical prediction is unambiguous, so there is no surprise to discover. Resources are limited, and applied quantum technologies pay better. But those explanations do not survive scrutiny. Quantum optics laboratories routinely perform experiments that are more technically demanding than the multi-stage eraser. Quantum computing groups manipulate dozens of qubits through hundreds of gate operations, maintaining coherence over timescales far exceeding what the multi-stage eraser would require. The argument that the theoretical prediction is unambiguous, that we already know what will happen, proves too much. We also knew that Bell inequality violations would occur before Alan Aspate ran his landmark experiment in 1982. We knew that the delayed choice experiment would confirm Wheeler's prediction before the Australian team did it in 2007. Aspect and the Australians ran the experiments anyway, because confirming a theoretical prediction in the laboratory is not redundant. It is essential. It is what makes a prediction into a fact, and the multi-stage eraser's prediction has never been made into a fact. There is a deeper issue here, one that touches the sociology of physics itself. Matthew Leifer, one of the few researchers actively working on retrocausal models, gave an assessment that is as honest as it is damning. There is a small group of physicists and philosophers that think this idea is worth pursuing, he said. I think other physicists are rightly skeptical, and the onus is on us to flesh out the idea. That sounds reasonable. That sounds like normal scientific caution, but read it again carefully. Leifer is not saying the idea has been evaluated and found wanting. He is saying other physicists are skeptical and that the burden of proof is on the retrocausality researchers. What he is not saying, because he is too diplomatic to say it, is that most of those skeptical physicists have never engaged with the retrocausality literature at all. They are skeptical of something they have not read, and the burden of proof is being placed on researchers who have already met it, in published, peer-reviewed papers, in reviews of modern physics and proceedings of the Royal Society and Physical Review A, papers that the skeptics are not reading. This is compounded by a confusion that Wharton and Price have tried repeatedly to correct, with limited success. Retrocausality keeps getting conflated with superdeterminism. The two ideas sound superficially similar, because both involve correlations between measurement choices and hidden variables. But they are fundamentally different in a way that matters enormously, and the conflation is not innocent. Superdeterminism says that the experimenter's choice of what to measure and the particle's hidden properties were both determined by a common cause in the distant past. When Aspect chose which polarization angle to measure in his Bell test, that choice was correlated with the photon's properties, not because the photon responded to the choice, but because both the photon and Aspect's brain were set on their respective courses by the initial conditions of the universe. Everything was predetermined. Free will is an illusion. And more importantly, the entire enterprise of experimental science is undermined, because every experiment you run and every free choice you make about what to measure was already scripted at the Big Bang. You cannot test anything independently because nothing is independent. Retrocausality says something completely different. The experimenter's choice is genuinely free. The particle's properties respond to the choice, but they respond backward in time rather than forward. The correlation between the measurement setting and the hidden variable is causal, running from the future measurement to the past particle, not conspiratorial, running from the ancient past to both. Free will is preserved. Experimental agency is preserved. The only thing that changes is the direction of one causal arrow. The distinction matters because superdeterminism is, by broad consensus, scientifically catastrophic. If you accept it, you can explain away any experimental result as a predetermined conspiracy, which means you can never learn anything new from data. Retrocausality is not scientifically catastrophic. It is merely deeply weird. It requires you to accept that causation can run backward in time, which is uncomfortable but does not undermine the practice of science. And the two ideas are not adjacent points on a spectrum, they are on opposite sides of a philosophical chasm. Confusing them is like confusing surgery with stabbing because both involve cutting. Yet the conflation persists. Wharton and Price, writing in The Conversation in 2010-3, described the problem directly. The retrocausality research community is still invisible to some experts in the wider field, and it gets confused for a different view called superdeterminism. When a mainstream physicist hears retrocausality, they think, oh, that is like superdeterminism. That is the idea that undermines free will and makes science impossible. And they dismiss it without reading further. The actual retrocausality papers, which go to great lengths to distinguish themselves from superdeterminism, never get opened. And this confusion is reinforced by the workshop circuit. There have been dedicated workshops on quantum retrocausation since at least 2011. The American Institute of Physics held a quantum retrocausation conference that year, and another in 2017. Cambridge hosted a retrocausality workshop in 2014. The University of San Diego held one in 2000. The Stanford Encyclopedia of Philosophy has a full entry on retrocausality, revised in 2203, cataloguing 7 concrete retrocausal models. This is not a fringe movement meeting in someone's basement. These are researchers at Cambridge and Princeton and Sydney, publishing in the best journals in the field, attending conferences organized by major institutions. But the workshops attract dozens of people, not hundreds. The publications are in philosophy of physics journals and reviews, not in Nature and Science. The experimental physics community, the people with the lasers and the beam splitters and the quantum memories, are not in the room. They are next door, working on quantum computing, and they have not been told that the experiment that could test the deepest question about the nature of time is sitting in their toolbox. There is also the matter of incentives. Academic physics runs on publications, citations, and grants. A successful multi-stage eraser experiment would produce a result that every theorist predicted, which limits its novelty value. But it would also produce data that forces the foundations community to confront questions it has been deferring for decades. And the foundations community is a small, underfunded, faintly disreputable corner of physics. The people who work on quantum foundations are sometimes regarded by their experimentalist colleagues the way a hospital regards its philosophy department. Interesting in principle. Not where the real work happens. An experimentalist who built the multi-stage eraser would produce a result that generates philosophical headlines rather than technological applications. In the incentive structure of modern academic physics, that is not a career move. It is a career risk. But that explanation, while true, is itself an indictment. It means that the structure of modern physics, the funding agencies, the journal hierarchies, the tenure committees, is specifically optimized to avoid answering the most fundamental question about the nature of time. Not because the question is unanswerable, not because the experiment is impossible, but because answering it does not advance anyone's career, and meanwhile the papers that approached the answer sit in the literature with single-digit citation counts. The Garisto-Hardy disentanglement eraser showing that entanglement itself can be destroyed and restored. Published in Physical Review A, available to anyone with a library card. Virtually unknown outside the specialist community. The Ramiz All-Islam Collective disentanglement eraser, showing that the erasure process can generate more entanglement than the system started with. Published in European Physical Journal D, fewer than 15 citations, the Brahman-Garbarino-Hayes-Mayer Chionic eraser, showing that neutral kaon systems offer unique temporal features for erasure experiments. Published in the Frascati Physics series, fewer than 10 citations. The proposed experiment at KLOE2 was never performed. The Aharonov-Zuberi review in Science, referencing Scully's unpublished results on quantum eraser microscopy, published in 2005, those unpublished results remain unpublished 20 years later. The Zuberi-Agarwal-Scully cavity QED disentanglement eraser, describing successive manipulations that cycle a system through states of entanglement and separability, published in Physical Review A in 2004. A proposal for iterated erasure in all but name, never experimentally implemented. And let me add one more. In 2018, Hatim Salih published a paper in Royal Society Open Science, Volume 5, Paper 171. 250, describing what he called a counterfactual quantum eraser. The protocol involves m outer cycles and n inner cycles of an interferometric procedure, an explicitly multi-cycle erasure structure embedded in a counterfactual communication framework. The paper combines the logic of the bomb tester with the logic of the quantum eraser and adds iteration. It is, as far as I can find, the closest anyone has come to a published multi-stage eraser protocol, and it sits in the literature, modestly cited, disconnected from the broader debate about retrocausality, unreplicated in the laboratory. This is not a single gap in the literature, it is a pattern. The quantum eraser was proposed in 1982. It was experimentally confirmed in 2000. Its extensions were proposed and partially confirmed over the following decade. And then the field stopped. Not because the questions were answered, not because the experiments were impossible, not because the theory was ambiguous. The field stopped because going further would have required facing implications that the mainstream was not ready to absorb. And the technology is right there. Let me be specific about this, because the "it is too hard" excuse needs to be examined against what quantum optics labs are actually doing right now. In 2020, a team at the University of Science and Technology of China, Jianwei Pan's group, demonstrated quantum entanglement distribution over 1,200 kilometers using the Messias satellite. That experiment required maintaining quantum coherence across the vacuum of space through atmospheric turbulence between a satellite moving at 8 kilometers per second and ground stations on opposite sides of a country. In 2023, IBM's Osprey processor operated on 433 superconducting qubits through thousands of gate operations. In 2021, a team at Harvard and MIT used a 256-atom programmable quantum simulator to solve optimization problems involving coherent manipulation of hundreds of quantum degrees of freedom simultaneously. The multi-stage quantum eraser requires one pair of entangled photons, one quantum memory, and a sequence of basis rotations on a single qubit. It is, by comparison, a modest experiment. The technical requirements are comparable to what a well-funded graduate student could build in 6 months to a year using commercially available optical components and an existing quantum memory platform. The fact that groups capable of distributing entanglement across 1,200 kilometers of space have not bothered to perform a 5-stage erasure on an optical bench in their own laboratory tells you something. And what it tells you is not about technology. That is the invisible scandal. And it is not invisible because it is hidden. It is invisible because it is sitting in plain sight, in the open literature, in papers with titles that practically beg to be read, and nobody is looking. There is one more thread to pull before we reach the bottom of this, and it takes us back to Wheeler. In 1990, Wheeler contributed an essay to a collection called Complexity, Entropy, and the Physics of Information, published by Addison Wesley. The essay was called Information, Physics, Quantum, and in it, Wheeler proposed what he called it from bit. The idea was that every physical quantity, every particle, every field, every space-time point derives its existence from answers to yes or no questions, from binary choices, from bits of information. The physical world is not made of matter or energy at its deepest level. It is made of information. This was not a metaphor. Wheeler meant it literally. He wrote that every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely from the apparatus' elicited answers to yes or no questions, binary choices, bits. The universe is not a collection of objects, it is a collection of answers. And the answers do not exist until the questions are asked. Wheeler's it from bit has been enormously influential. It inspired the entire field of quantum information theory. It influenced John Preskel's work at Caltech. It shaped the thinking of Leonard Susskind, whose work on the holographic principle and black hole complementarity owes a direct conceptual debt to Wheeler's insight that information is more fundamental than matter. It led, through a chain of intellectual descendants, to the now serious proposal that space-time itself emerges from quantum entanglement, a line of research associated with Mark van Ramsdonk, Juan Maldacena, and the ER equals EPR conjecture. But Wheeler's own version of it from bit was more radical than any of these descendants. Because Wheeler was not just saying that information is fundamental, he was saying that the information is created by measurement. The bits do not exist before the questions are asked. The universe does not contain pre-existing answers waiting to be discovered. It contains potentialities that become actual only when an observation collapses them into definite outcomes. And the observation is itself a physical process within the universe, which means the universe is generating its own information, answering its own questions, calling itself into existence through a recursive loop of observation and actualization. That is the self-excited circuit. That is the you with the I at the end, bending back to look at itself. And here is what happens when you combine it from bit with the quantum eraser. If every physical fact is an answer to a question, and if the quantum eraser can erase the question, then what happens to the fact? The signal photon hits detector D0 and produces an electrical signal. That electrical signal is a physical event. It is an it. According to Wheeler, it derives from a bit, an answer to a yes or no question. The question is, did the photon travel through slit A or slit B? If the question has a definite answer, the which path information exists. The photon is a particle and there is no interference pattern. If the question has no definite answer, the which path information has been erased. The photon is a wave and interference appears. The quantum eraser shows that the answer to the question can be deleted after the it has already been recorded. The physical event at D0 has occurred. The electrical signal is in the file, but the bit that gives the event its meaning, the answer to the which path question, is not yet determined. It depends on the idler measurement, which has not happened yet. The it exists without its bit. The fact exists without its meaning. The event has occurred, but what the event was has not been decided. In the multi-stage eraser, this indeterminacy is not brief. It is not the 8 nanoseconds of the Kim-Shih experiment. It persists for as long as the idler sits in the quantum memory, undergoing its cycles of erasure and restoration. Each cycle toggles the answer. Yes, the photon went through slit A. No, the question has no answer. The photon went through both. Yes, slit A again. No, both again. The bit flickers on and off like a fluorescent light in a horror film, and the it, the physical event at D0, sits there patiently, waiting for the flickering to stop so it can find out what it is. Wheeler would have loved this, and Wheeler would have been disturbed by it, because it from bit is supposed to be a statement about the deepest level of reality, and the quantum eraser suggests that the deepest level of reality is not stable. The bits that give the its their existence are not permanently written. They are written in pencil. And someone in the future is holding the eraser. There is a thermodynamic dimension to this that makes it even more uncomfortable. In 1960, Rolf Landau at IBM published a paper arguing that the erasure of one bit of information necessarily generates at least kT times the natural logarithm of 2 in heat, where K is Boltzmann's constant and T is the temperature. This is Landauer's principle, and it has been experimentally confirmed. It connects information theory to thermodynamics. At the most fundamental level, erasing information has a physical cost. It produces entropy. It is an irreversible act, at least thermodynamically. Now apply Landauer's principle to the multi-stage quantum eraser. Each cycle of erasure Each time you rotate the idler state from the witch path basis to the superposition basis, costs at least kTln2 in dissipated energy. Each restoration costs the same. 10 cycles cost 10 times as much. 100 cycles cost 100 times as much. The thermodynamic arrow of time accumulates with every cycle. Heat flows into the environment. Entropy increases. The laboratory gets warmer by an infinitesimal measurable amount. And yet the quantum state of the signal photon's data remains indeterminate throughout. The thermodynamic arrow of time marches forward with each cycle, because erasure is physically irreversible. But the informational character of the past, the question of whether the signal photon belongs to the interference subset or the non-interference subset, remains suspended, undecided, unwritten. No matter how many cycles of thermodynamically irreversible operations have been performed on the idler, this is the deepest tension in all of physics, sitting right there in the multi-stage eraser. Thermodynamics says time has a direction. Information flows toward equilibrium. Entropy increases. The past is the low entropy state, and the future is the high entropy state. That arrow is real. It is physical. You can measure it in the waste heat of Landauer's erasure. But quantum mechanics says the informational content of the past, the bits that define what happened, are not bound by that arrow. The thermodynamic cost of each erasure cycle accumulates forward in time, but the meaning of the signal photon's detection does not accumulate at all. It stays suspended. It stays open. The thermodynamic past gets more and more fixed with each cycle, because each cycle dumps more entropy into the environment. But the quantum past stays exactly as unfixed as it was after the first cycle. Two arrows of time, one pointing forward, accumulating irreversibility. One pointing nowhere at all, suspended in superposition. And both of them are real, in the same experiment, at the same time, describing the same system. Nobody has measured this. Nobody has built the apparatus that would let you watch the thermodynamic arrow accumulate while the quantum arrow refuses to commit. The experiment would be more than a test of retrocausality. It would be a direct confrontation between the two deepest frameworks in physics, thermodynamics and quantum mechanics, in a single apparatus on a single optical bench. And it has never been done. Now bring in Price's time symmetry argument. If the laws are time symmetric, and the bits are determined by measurements, and measurements can occur in the future relative to the events they define, then the arrow of time is not a fundamental feature of reality. It is an artifact of the way we process information. We experience time as flowing from past to future, because our memories are structured that way. But the physics does not require this. The physics is equally comfortable with influence flowing from future to past. And the quantum eraser is the laboratory demonstration that this backward influence is not hypothetical. It is real. It is confirmed. The only question is how far it extends. Wharton's framework makes this explicit. In his Lagrangian picture, the universe is a four-dimensional boundary value problem. The initial state and the final state jointly determine the solution. There is no preferred direction of time. There is no fundamental distinction between a cause and an effect. There is only the self-consistent solution, the one configuration of all events that satisfies all the constraints simultaneously. The past is not built from the past. The past is extracted from the whole, which includes the future. And Sutherland's causally symmetric Bohm model makes it concrete. Each particle has a definite trajectory, but that trajectory is guided by influences from both past and future. The pilot wave propagates in both temporal directions. The particle is like a boat navigating a river with currents flowing both upstream and downstream, and its path is determined by the combined effect of both currents. Change the downstream current, the future measurement, and the boat's path changes, including the stretch of river it has already traveled. All of these frameworks are internally consistent, All of them reproduce the predictions of standard quantum mechanics. None of them have been refuted. And all of them make the same prediction about the multi-stage eraser. It will work. The past will remain indeterminate for as long as the idler is held in quantum memory. The number of erasure cycles will not matter. The photon will patiently wait for its future to be decided, no matter how long it takes. And nobody has tested this. There is a way to understand the reluctance, if not to excuse it. The history of physics is full of experiments that were avoided not because they were difficult, but because the community was not ready for the implications. David Bohm published his pilot wave interpretation in 1952, providing a fully deterministic, realistic account of quantum mechanics that reproduced every prediction of the standard theory. It was ignored for decades. John Bell himself, who is now considered one of the greatest physicists of the 20th century, wrote a paper asking why Bohm's theory was still being dismissed by textbooks 26 years after its publication. Why did people go on producing impossibility proofs after 1952? Bell asked. And as recently as 1978. Bohm, who had already been driven out of the United States by McCarthyism and forced to build his career in exile in Brazil and then London, reportedly told a colleague that he was tired of answering objections from people who had never seriously studied his work. The pattern is consistent. Hugh Everett published the Many Worlds interpretation in 1957. It was dismissed. It took decades to gain any traction, and Everett left physics entirely, became a defense contractor, developed a drinking problem, and died of a heart attack at 51. His daughter committed suicide years later, leaving a note asking that her ashes be thrown in the trash, so she could end up in the same place as her father. Everett had asked that his own ashes be thrown in the trash, having given up on a physics community that refused to engage with his ideas. Costa de Beauregard was forbidden from publishing by his own advisor. Bell spent years arguing for the importance of foundations work at a time when the field was considered disreputable. Bohm was exiled, Everett was broken. And in each case, the pattern was the same. The heterodox idea was not refuted, it was not shown to be wrong, it was not contradicted by experiment. It was simply ignored. The mainstream did not say, "We have examined this and it fails." The mainstream said nothing at all. It continued publishing textbooks that presented the Copenhagen interpretation as the only interpretation, continued granting tenure to physicists who worked on problems the establishment considered real, continued funding experiments that the establishment considered worthwhile. The heterodox ideas existed in the literature, technically accessible to anyone with a library card, but practically invisible because nobody assigned them, nobody cited them, and nobody talked about them at conferences. This is how a field buries an idea without dirtying its hands. You do not need a conspiracy, you do not need a committee that meets in secret to decide which ideas to suppress. You just need a culture where asking certain questions is a career risk, where the most prestigious journals prefer papers that extend existing frameworks rather than challenge them, and where the funding agencies reward technological applications over foundational inquiry. The suppression is structural, not intentional. And it is almost perfectly effective because the ideas that are ignored cannot fight back. They have no constituency. They have no champions in positions of power. They sit in the literature, waiting, and nobody comes. The Retrocausality program is in this position right now. Wharton has tenure at San Jose State, not at MIT or Caltech or Princeton. Price is emeritus at Cambridge, which gives him freedom but not influence over the next generation. Sutherland is at Sydney, working largely alone. Leifer is at Chapman University, a small private institution in Orange County, California. These are not marginal scientists. They are rigorous, published, peer-reviewed researchers whose work appears in the best journals in the field, but they are institutionally peripheral. They do not train the graduate students who become the next generation of experimentalists. They do not sit on the grant committees that decide which experiments get funded. They do not write the textbooks that shape how undergraduates think about quantum mechanics. And the experiment they want to see performed requires an experimentalist with access to a quantum optics lab, which means it requires someone at exactly the kind of institution where the retrocausality program has no foothold. The physics community does not reject heterodox ideas by refuting them. It rejects them by ignoring them. And when the heterodox idea is attached to an experiment that could actually test it, the community ignores both the idea and the experiment. The multi-stage quantum eraser is the latest entry in this tradition. It is not that physicists have examined the experiment and concluded it would be uninformative. It is that they have never examined it at all. The papers that propose it, or come close to proposing it, sit in the literature unread. And the theorists who argue that its results would be profoundly meaningful, Wharton and Price and Sutherland and Leifer, publish their work in respectable journals and attend their workshops and are treated, for the most part, as an interesting but marginal curiosity. This is the way the invisible scandal works. It does not require a conspiracy. It does not require anyone to suppress anything. It only requires a system where the incentives for asking certain questions are smaller than the incentives for not asking them. And in modern academic physics, the incentives for probing the nature of time are vastly smaller than the incentives for building a quantum computer, or detecting gravitational waves, or pinning down the Higgs boson's coupling constants. The multi-stage eraser would not produce a patent. It would not launch a startup. It would not generate a Nobel Prize, because the Nobel Committee does not give prizes for confirming theoretical predictions about the foundations of quantum mechanics, no matter how profound. It would produce only a result that makes the physics community uncomfortable. And uncomfortable results, in a field that runs on grant cycles and tenure clocks, are not a product anyone is buying. So here is where we are. After 25 years of the quantum eraser being debated in YouTube comment sections and physics classrooms and popular science books, after thousands of citations and hundreds of explainer videos, and an entire cottage industry of debunking and counter-debunking, the actual experimental program stalled at the first stage. The Kim-Shih experiment was the beginning, and the field treated it as the end. The extensions that Garisto and Hardy proposed, that Zuberi and Agarwal and Scully designed, that Brahman and Garbarino and Hismire imagined for kaons, that Sally embedded in a multi-cycle protocol, were published and then left alone. The multi-stage eraser, the experiment that every interpretation of quantum mechanics predicts would work, the experiment that would force the foundations community to choose between deeply uncomfortable alternatives about the nature of the past, has never been built. And Wheeler's question remains unanswered. Does the past exist as a fixed objective fact, or is it under construction, perpetually, by the future? The retrocausality camp says the future constructs the past. The mainstream says the question is not well defined. The debunkers say there is nothing to explain, and the experimentalists have never produced the data that would settle the argument. Think about what that means. There is a question about the nature of time that was formulated precisely enough to test in a laboratory. The test was partially performed. The partial results were striking enough to generate decades of debate. The full test was designed, or nearly designed, in multiple independent theoretical papers, and then nobody ran it. It is as if someone drilled an oil well, hit something at 100 feet, argued about what it was for 25 years, and never drilled to 200 feet. Not because the drill was broken, not because the ground was too hard, but because nobody wanted to find out what was down there. And this brings us back, finally, to the question that started this entire line of research. To a man who lost his brother in a foxhole in Italy, and spent the rest of his life asking whether the past was fixed. Wheeler's relationship with this question was never purely academic. You can trace it through his career like a fault line running through rock, sometimes invisible on the surface, but always there, always shaping the landscape above it. After the war, he threw himself into nuclear physics, into general relativity, into the structure of space-time. He supervised Feynman's thesis on the path integral formulation, which describes a particle as taking every possible path simultaneously. He supervised Everett's thesis on the many worlds interpretation, which says every quantum measurement splits the universe into branches where all outcomes occur. He developed the concept of quantum foam, the idea that at the Planck scale, space-time itself is a roiling chaos of virtual wormholes and geometry fluctuations. Each of these contributions, in its own way, chips at the solidity of the past. If a particle takes every path, which path did it really take? If every outcome occurs, which outcome really happened? If space-time is foam at its foundation, what does it mean for an event to have a fixed location in a fixed past? Wheeler never said publicly that these questions were personal. He was too disciplined for that. But the delayed choice experiment, which he proposed in 1978, is the one that cuts closest to the bone. Because the delayed choice experiment does not merely say that the past is strange at the Planck scale, or in many worlds branches you will never visit, or along paths a particle might have taken but did not. It says the past is strange here, in this universe, at the scale of real photons hitting real detectors. And the strangeness is not abstract, it is operational. You, the experimenter, make a choice, and that choice determines what the photon did before you made it. The cosmic version makes this personal in a way the laboratory version does not. Wheeler imagined a photon from a distant quasar, emitted when the universe was young, traveling for billions of years across the void. It passes a gravitational lens, a massive galaxy that bends its path, sending it around both sides simultaneously, or one side specifically, depending on how the astronomer chooses to observe it. For billions of years, that photon was traveling. And today, right now, a human being on Earth decides how to measure it, and that decision retroactively determines the photon's path for the last 10 billion years. Wheeler chose this example deliberately. The timescale matters. 8 nanoseconds in a laboratory is one thing. You can dismiss it as a quirk of entanglement, a technicality of quantum mechanics that does not really touch the macroscopic world. But 10 billion years is not a technicality. 10 billion years is the age of stars. It is the time span in which galaxies formed, planets coalesced, life emerged, primates evolved, and a human being developed the intelligence to build a telescope and point it at the sky. And the act of pointing that telescope, the conscious choice of how to observe, reaches backward through all of that history and writes the photon's path as if it had always been that way. If Wheeler thought about Joe when he wrote those words, he never said so. But the structure of the thought experiment is a mirror of his grief. A choice made now, an observation performed today, determines what happened in the deep past. If John had worked faster, if the bomb had been ready sooner, if the war had ended a year earlier, Joe would not have died in that foxhole. But those are counterfactuals. In the classical world, counterfactuals are just stories. What happened, happened. In Wheeler's quantum world, counterfactuals are part of the physics. What could have happened constrains what did happen, and what will happen can retroactively reshape what already occurred. John Wheeler died on April 13, 2008, at the age of 96. He spent his last years at Princeton, increasingly frail, but still lucid, still asking questions. He never got to see the retrocausality research program mature. He never saw Price and Wharton's review in Reviews of Modern Physics. He never saw Leifer and Pusey's result in Proceedings of the Royal Society. He never saw the extension papers that pushed the quantum eraser beyond the standard experiment, and he never saw the multi-stage eraser performed, because it has not been performed. But the question he spent his career asking, the question that began with a postcard saying, "Hurry up," and a death in Italy and a lifetime of guilt and grief, that question now has a possible experimental answer, not a definitive answer. No single experiment can definitively prove that the future rewrites the past, because the no-signaling theorem ensures that retrocausality, if it exists, operates behind a veil of statistical indistinguishability. But the multi-stage eraser would demonstrate concretely and repeatably that the past has no fixed character on timescales that can be extended without limit. That the signal photon's history is a function of an arbitrarily long chain of future operations. That the bits that define the its are provisional, erasable, restorable, and re-erasable, with no endpoint. If that result stands, and quantum mechanics says it will stand, then the past is not what you think it is. The past is not a thing that happened and was recorded and is now permanent. The past is a set of correlations that have been partially constrained by the present, but remain open to revision by the future. Your memories are not fixed inscriptions. They are provisional annotations in a document that the universe has not finished writing. Every measurement that will ever be made by anyone, anywhere, at any point in the remaining lifetime of the cosmos has the potential to retroactively adjust the meaning of everything that came before it. Not the events themselves which are recorded, but the character of those events which is not. Think about what you did today. You woke up, you made decisions, you interacted with objects and people and systems that are, at their most fundamental level, quantum mechanical. The atoms in your coffee cup, the photons from your screen, the electrons firing across your synapses, all of them are described by quantum mechanics. All of them have wave functions. All of them are entangled to varying degrees with the rest of the universe. In the standard picture, none of this matters at the macroscopic level. Decoherence kills quantum effects long before they reach the scale of coffee cups and synapses. Your past is your past. It happened. It is fixed. But decoherence is not a fundamental principle. It is a practical one. It describes what happens when quantum information leaks into an environment with a vast number of degrees of freedom, making it effectively impossible to track or recover. Effectively impossible is not the same as impossible. It is a statement about our ability to control the environment, not about the laws of physics. The laws of physics say that the information is still there, scattered across the environmental degrees of freedom, technically recoverable by an observer with sufficient control. Landauer's principle says that recovering it would cost energy. The second law of thermodynamics says that the cost is prohibitive for any macroscopic system. But prohibitive is not a law. It is an engineering constraint. And that means the openness of your past, the degree to which future measurements could in principle revise its character, is a question of degree, not kind. The signal photon in the Kim-Shih experiment has a maximally open past because the idler photon is under perfect quantum control. Your past is almost completely closed because the information about it has leaked into trillions of environmental degrees of freedom. But almost completely is doing work in that sentence. The gap between almost completely closed and completely closed is the gap between a practical description and a fundamental one. And the fundamental description says your past is not closed. It is very, very nearly closed, but not all the way. That is not a comfortable thing to sit with, and the multi-stage eraser is the experiment that would demonstrate, on a laboratory bench, that the gap is real, that the openness of the past is not a theoretical curiosity, but a measurable physical property, that the number of times the past can be revised has no fundamental limit, that the only thing protecting the fixedness of your personal history is the practical impossibility of controlling trillions of environmental degrees of freedom, not any law of physics that says the past must be fixed. This is either the deepest truth about the nature of reality or the deepest misunderstanding. And the experiment that could tell us which one it is has been available for over a decade, has been partially designed in papers that almost nobody has read, and has never been performed. Wheeler asked whether the past is fixed. Scully built the apparatus that could test it. Kim ran the first stage, and then the field stopped, and the question was left open, and the papers that could have led to the answer accumulated their single-digit citations and were quietly forgotten. Joe Wheeler died in a foxhole in Italy in 1944. That happened. That is a fact. But in a universe where the past is not fixed, where the bits that define the its are written in pencil, where the future has a say in what the past means, the question of what Joe's death was, what it meant, what it led to, what it changed, is not settled by the event itself. It is settled by everything that comes after, by John's work on the bomb, by the delayed choice experiment, by the extensions that were published and forgotten, by the experiment that has not yet been run, and by whatever the universe decides to do with the information long after every physicist involved has died. The past does not end, it does not close. It sits there, open, patient, waiting for the future to finish telling it what it was. And the experiment that would prove this, the experiment that would show the past being rewritten over and over on a laboratory bench, the experiment that every interpretation of quantum mechanics agrees would work, has never been performed. The drill hit something at 100 feet. The readings were extraordinary, and the drilling stopped, and the hole is still there, open, waiting, and nobody is looking down.